Okay, hello everyone. This is Shiming from the Hong Kong Polytechnic University. And today I'd like to present our recent work on the orthogonal LoRa communication. This is a collaborative work with Tsinghua University. Recent years, the low-power wide area network has enabled various IoT applications such as the smart agriculture, smart logistics, smart city, and smart metering. And featured by the long-range communication, LoRa has been a dominating technology of LP1. Till this year, there have been around 7 million gateways and more than 400 million end nodes with LoRa deployed worldwide. And to serve a large-scale IoT network, long range itself is not enough because the large footprint can cover massive LoRa nodes with diverse link conditions. Like in an IoT network, we need to connect thousands of LoRa nodes, and the distant LoRa node can have very poor signal quality. So to serve such requirements, LoRa provides diverse and flexible logical channel settings for the massive IoT communication. For example, a LoRa node can select different bandwidths to occupy a spectrum and use different spreading factors to modify the symbol duration. And the different spreading factors can communicate simultaneously on the same frequency, and for this feature, we call it orthogonal. So to understand this, in LoRa, when we demodulate a packet, it actually logs on a specific logical channel. For example, this figure shows a LoRa chirp, a symbol chirp, and when we receive it, we first multiply with a locally generated down chirp, and then we perform FFT. And the single tone will be converted to a peak at the frequency domain and enjoys a specific SNR gain. And what if there is a concurrent logical channels, like a different spreading factor? As the concurrent channels does not share the same frequency chirp slope with the local down chirp, and it will not be demodulated and act as the noise floor. The signal energy still spread across the spectrum. And by leveraging the SNR gain, we can separate concurrent logical channels by the receiver naturally. And by leveraging the orthogonal logical channels, for example, the COS gateway can cover 8 concurrent physical channels, physical spectrums. And when we consider different spreading factors, we can get 56 logical channels. And the LoRa node can access the network with different logical channel settings. And with the many logical channels, we can enable the reliable channel, flexible channel access, adaptive data rate, and ultra-high concurrency for the LoRa network. And the logical channels can empower a massive IoT connectivity and high spectrum efficiency. And here we ask a question, are these logical channels really orthogonal? You may consider, we have talked a lot about the orthogonal logical channels. Why do we ask this? Actually, before this research, we do not have this question. But when we actually reach out the campus and deploy a city-scale LoRa network, we find something unexpected. Here, we find that the distant LoRa node can originally connect to the gateway, but they get lost as the network scales. And when we zoom into the log of the LoRa gateway, we find that most of the high spreading factor packets are lost. Actually, when we originally find these issues, we do not know why. So we replace the commodity LoRa gateway with our SDR to zoom into the physical layer, and we want to look for the reason. And ideally, we expect the concurrent logical channels would exhibit like this. One with the SNR gain, another spread across the spectrum as it is designed by the LoRa. But this is actually what we find. We can only see the noise. We cannot find the peak we want or we expect. So after we make the analysis and a lot of measurement, we find that for the ideal or the design of LoRa network, we have a strong assumption for the orthogonality that the logical channels should have the similar signal strength. So in this case, if one logical channel we target can enjoy a gain, others stay at the spectrum, and we can explicitly get what we want as it can stand out from others. But the fact is that the LoRa network has a very large footprint, and they can have the near-far effect and the power disparity across the concurrent logical channels. So when we receive the logical channels with power disparity, the strong logical channels can raise the noise floor when we receive the weak logical channel. For example, this is a very common case in LoRa where a strong packet can have like 5 dB above the noise floor, but the weak packet can be from the distant LoRa node can be below the noise floor. And the near-far effect would break the orthogonality between logical channels. And for this problem, we call it logical channel interference. And here I want to make a remark for the problem difference between the previously researched problem of the collision. For the collision problem is that the different nodes transmit with the same spreading factor and same bandwidth on the same frequency. But for the logical channel interference, it targets the different spreading factors. And in the collision problem, we can see the explicit symbol collisions that we cannot separate from. We have multiple peaks detected, and we cannot separate them. But in the logical channel interference, the strong packet will raise the noise floor, and we cannot find the weak ones. We cannot see any peak from the results. And many of the state-of-the-art in the LoRa community focused on the collision problem, but no prior works have explored the logical channel interference problem. And you may ask, they don't work on this. Is it because this is not a severe problem? And also, we have more measurements in our testbed to explore the severity of the logical channel interference. And here we can see, actually, especially when we want to deploy a large-scale LoRa deployments with hundreds of nodes, we can see the collision problem is much less than the logical channel interference problem because the concurrent nodes typically use different spreading factors to access the network. And I select one of the state-of-the-art research work to decode the collision, and we can see these works can, to a large extent, to recover the collision packets and receive these packets. But for the logical channel interference, the existing works cannot work on this problem, and it is largely overlooked. And here I want to make highlights about our measurement results. That actually, the logical channel interference problem comes from the near-far effect. And it is a very common scenario in the LoRa deployment. And this is a severe problem, especially when we want to deploy a large-scale network with hundreds of nodes. And the existing works largely overlook this problem, partially because this is not as explicit as the collision problem. So in this work, we present our system canvas to resolve this problem and orthogonalize these logical channels. So for the basic idea, first, I have to introduce why the standard LoRa demodulation fails for these scenarios. It is because when we receive the weak logical channels, it will experience a special gain after demodulation. But there is a concurrent strong logical channels that increase the noise floor. So even if the weak one enjoys an SNR gain, we cannot get it after we demodulate. And this is a root cause of the interference problem. And so in our system, we propose an interference cancellation technique that before we receive the weak logical channels, we first apply a cancellation to suppress the energy of the strong logical channel. And then after suppress it to the noise floor, we can leverage the gain of the LoRa demodulation to receive the weak one. And that's our solution. But a follow-up question is, how can we achieve this interference cancellation? A naive idea is, if we have the raw signal of the strong logical channel, we can just remove it from the receiver, from the whole RX signal, and we can get the weak one. But it is not that direct, because the logical channels are interleaving with each other, so it is hard to directly get the logical channel 1. It is the strong one. So that's the problem, and we propose our insight is that the strong logical channels is less interfered by the weak ones. So we can first receive the strong one and reconstruct its raw signal, and then remove the raw signal from the RX signal, and we can get the weak one and then receive the weak one. And by applying this iterative cancellation approach, we can receive the signals from the strongest to the weakest. And this is our system workflow. And when we have an aggregated logical channel, we can first receive the strong one, and we have to capture the physical layer footprints of the strong logical channel and reconstruct its raw signal, and then remove and iteratively receive all of the logical channels concurrently. And for the cancellation process, we call it logical channel interference cancellation for LoRa. And the biggest challenge is in LoRa, LoRa has a very long packet duration and symbol time. It is much more challenging than the traditional wireless signal like the Wi-Fi and Bluetooth, because a LoRa packet can last like hundreds of milliseconds, and the channel we can experience channel variation, and the LoRa signal is transmitted by the low-cost hardware. We will experience like the signal drift and frequency offset. We have to replay all of these signal offsets on the reconstructed LoRa signal to make it feasible for the reconstruction and cancellation. And it is very challenging. Here I will introduce one of the technical challenge. It's the phase drift. When LoRa modulates a symbol, it actually has a cyclic frequency shift after it reaches the maximum, and it will cyclic shift to the minimum frequency and then increase. It is 2 chirp segments. And between the 2 chirp segments, there is a random phase drift. As you can see from the figure, the phase is inconsistent. And in traditional LoRa demodulation, we just use the D chirp and FFT, get one frequency peak. And if we use this peak and its phase information to reconstruct this chirp and remove it, we can see the result. The chirp is not fully suppressed. The reason is that the phase misalignment will introduce significant challenge for the cancellation. It is not effective. So this is a unique challenge for the reconstruction and cancellation, but not for the demodulation itself. So to resolve this problem, our insight is that even if there is a phase drift between the 2 segments, the phase within each segment is consistent. So to achieve an effective reconstruction, we first upsample the chirp to a higher sampling frequency. And we can see after we perform the D chirp, the 2 chirp segments will be converted to 2 independent peaks. And they have, we can separate their phase, and we can leverage the phase difference of these 2 peaks to reconstruct a new chirp. The chirp faithfully represents the phase drift of the original signal. And after the interference cancellation, we can see the right figure. The chirp is effectively canceled. So that's our solution. And we have many other techniques in our full paper, like how to address other signal offsets, like the carrier frequency offset, and how to track the channel fluctuation within a LoRa packet, and how to integrate with the existing collision recovery techniques to handle the hybrid interference cases. And if you are interested, you can refer to our paper for details. And for the time limit, I have to skip them. And for the evaluation, we implement our system around our campus with 50 LoRa nodes, test bed, and both commodity gateways and USRP to evaluate our system. And first, let's see the logical channel interference cancellation performance. Here, this figure shows a step-by-step gain. That's how much gain we can get from to compensate for the CFO, compensate for the channel fluctuation, and until the final step. And this figure shows the weak packet reception performance, where we disable the interference signal to represent the performance of perfect cancellation, where which is the sensitivity of the pure weak packet reception, and we compare it with our practical performance under a logical channel interference. We can see after we cancel the strong signal, there is only a less than 1 dB sensitivity loss when we receive the weak packet. And for the logical channel concurrency, we compare our system with the baselines of the collision recovery techniques. And we can see the existing works cannot handle such cases that the different spreading factors are transmitted simultaneously. And here, our system can improve the concurrency performance per unit frequency, especially when the different spreading factors are transmitted concurrently. And here is the large-scale network scaling performance, and we compare our work with the collision recovery and auto configuration, like the gateway with massive logical channels. And we can see, due to the logical channel interference, the existing work suffers from the packet loss, especially for the outdoor deployments, that the nodes has a very large distribution on the physical range and with diverse link quality. And our system can boost the state-of-the-art by 80%, especially for the outdoor performance, where we can address the near-far effect in the network deployment. And we can complement with the state-of-the-art because we solve a different problem and bring the gain from a new dimension. And especially, we can enhance the system performance for the outdoor deployments. And more evaluations, like a larger scale network with different duty cycle, and how we can perform like different SIR interference ratio, and the time overhead of our system. If you are interested, we have experiments in our full paper for your reference. And here I want to have there is something to take away with this talk. First, LoRa logical channels are not truly orthogonal as it is designed originally. And the logical channel interference problem is very severe in the LoRa deployment, especially we target a large-scale deployment with massive hundreds of, even thousands of LoRa nodes. And we present our system canons to practically orthogonalize these logical channels and brings a significant gain than the state-of-the-art, especially for the outdoor deployments. That's all for this talk, and we have our artifact available on the GitHub, and you can refer to our code, and we can have future collaborations. And thank you for your attention. I'm happy to take any questions.
Hello, thank you for a great talk. I have one question. Is your work is like use NSRP as a gateway. So did you consider can we use like a commercial gateway to as you like how do we to make more commercial solution?
Yeah, thank you for the answer. So the reason we use the USRP is that when we want to do something like the interference cancellation and reconstruction, we have to access the raw signal of what we receive. But the commodity gateway does not provide this interface for us. So we currently this version can only apply to the USRP gateway. And in the future, if the commodity gateway can provide like the interface for the raw signal and provides additional like the digital signal processing actions for us, so we can deploy our algorithm on the commodity gateway.
Okay, thanks. Second question is about your methods. It's like how your methods like if we have different communication distance, is your method still work and like that? Like how the SNR change? How about your method performance? Because I think the SNR is very like if the SNR is very low, like could be lower than the noise floor, but it still can work.
Yeah, of course. Our system targets the different SNR that represents different communication range, because the long range node has a very low SNR, and if it's within 100 kilometers, the signal quality is kind of good. So our system mainly targets the concurrent communication with different and diverse SNR from the 20 dB, it's a very high quality, to minus 20 dB with ultra low signal quality. Yeah.
Okay. Final question is about usually for a concurrent transmission. Usually we also have like a MAC or MAC solution, and you're basically more about physical solution. Can we like can you, in your experiment, do you need to consider the MAC levels? You need to integrate some MAC level solution to increase your network throughput scale, something like that.
Yes, of course. Thank you for the question. Actually, for the MAC layer solutions like the LMAC in MobiCom 2020, they just regard the different spreading factors as the orthogonal, and they perform like the channel scheduling for the end nodes. But this is actually not, and our work is to bridge the gap or make it truly orthogonal, make the spreading factors or logical channels truly orthogonal. Actually, they can work together to improve the LoRa network.
Okay, so you will dynamically to set the SF for, right? Use the LMAC solution?
Yeah.
Okay, thank you. That's my question.
Let's thank our speaker one more time.